Hello students, in this one we're going to be talking about some determinants, which is a special number that we use in matrices, and how to find inverses in matrices. This is going to get into dealing with inverse operations like we've been doing with numbers for years, and how we can use that with matrices to solve problems. First off, we're going to do some multiplication. This is going to do two things. One is going to help us remember how to multiply matrices, and the other is to kind of see what's going on here. So if I'm doing A times B, I'm going to do the row times the column. So I'm going to call it row 1, column 1. That's going to be 0 plus 1 is 1. Okay, then row 1, column 2. That's going to be 0, okay, plus 0. Oh, that's not bad. Then we do row 2, column 1. That's going to be -1 plus 1 is 0. Okay. And finally, we're going to do row 2 times column 2. That's going to be 1 plus 1 times 0, 0 is 1. So A times B would be this matrix 1, 0, 0, 1. We learned in our first video that matrices were not commutative. So it means that going forwards and backwards doesn't necessarily mean the same thing. Let's see what happens if we do B times A. So that would be row 1 times column 1 this way. That ends up giving us 1. Row 1, column 2 is going to give us 0. Row 2, column 1 is going to give us 0. And row, switched over to eraser there. Row 2, column 2 is going to give us 1. So that's interesting. For whatever reason, this gave us the same answer both ways, which is unusual for matrices. We're going to do the same thing with C and D. We're going to multiply these one way, just to kind of see what happens. And when I do that, I've got -4 plus half of 10 is 5. Okay, that's 1. Same thing. We've got 2 plus -2 is 0. Then row 2, column 1. -10 plus 10 is 0. And then row 2, column 2. All right, so that's going to be +5, and -4 is 1. We got the same matrix again. So what we're discovering is that some matrices, when you multiply them together, give you this weird matrix. I think we got one more multiplication to play with before we figure out something special about this. We do. And that's going to be multiplying that special matrix by something. So if I do row 1, column 1, that's going to give us 2. Row 1, column 2, that's going to give us -1. Row 2, column 1, -10. And row 2, column 2, that gives me 4. We get the same matrix spit out of this that we did going into this, which is kind of weird. So what we discover is that multiplying by this matrix 1, 0, 0, 1 gives us the same matrix back out. What that suggests for us is that we have this thing called an identity. Think about when you're multiplying numbers like 1 times 9.73. We get 9.73 out, and we call 1 the multiplicative identity. In matrices, this is our multiplicative identity, and we're going to multiply this by any matrix that can be multiplied by this. So that's anything that has 2 rows for us to deal with. If we multiply by this matrix, we end up getting a value that works. Another way to think about this is that in dealing with normal numbers, if we have something like 1 times 1, sorry, let's go with 9 times 1/9. When we multiply those, we get that identity. That's kind of what we were seeing with the first examples we looked at. When we multiplied those matrices, we got 1 as an answer. We call 9 and 1/9 multiplicative inverses, and when we multiply them, we get 1, the identity, as a solution. Each of these following things does not have an inverse. Take a minute and see if you can notice any kind of patterns in these numbers, because there are some patterns. They're a little bit difficult for us to see. Hopefully you paused the video there. One of the things that you might notice is that if I were to take a look at these numbers, the numbers are related to each other. So like if I take a look at 2 and 6, I have to multiply by 3 to get there. 3 is part of that. Same for the next one. To get from -5 to 10, 2 is part of that. They're all 6s, 2s and 3s in both diagonals. Diagonals are kind of interesting here. And one of the things I notice, if I do 2 times 3, that gives me 6, and then 6 times 1 is also 6. We get -20 this way, -20 going this way. 36 and 36, -6 and -6. We've got +10, +10. The product of the diagonals is equal in all of these things. So I'm going to call this the product of diagonals is equal. Yeah, that's kind of a weird thing for us. There's a characteristic of this that makes it impossible for us to find an inverse. All right. So we're going to use matrix multiplication to figure out how to make an inverse from this thing. I'm also going to do something kind of weird, which is not simplify anything, which will help us with solving some of these things. So starting this out, we've got 1 and 2 times A and C, respectively. So let's just kind of do this as row 1, column 1. That's going to be 1A plus 2C. All right, row 1, column 2. We're going to have 1B plus 2D. Then let's do row 2. Row 2, column 1. That's going to give us -5A plus 7C. And then row 2, column 2, we have -5B plus 7D. Okay. What we know is that this matrix that we just made is equal to the matrix 1, 0, 0, 1. That lets us make some matrix equations. So for example, I could say 1A plus 2C is equal to 1. That's my first thing. -5A plus 7C is equal to 0. We can use this to try then to solve the system of equations, and you might notice that we can do some substitution here, or we can do some elimination. I might multiply this whole thing by 5, so we get 5A plus 10C is equal to 5. When we add those together, we get 0. I don't know what that is. That's supposed to be 10C. That's interesting. We get 17, and we get 5. So that means that C would be 5 over 17. Okay, I'm just going to put this way over here somewhere. And then I'm going to take a look at that and try to find A for that. So if I've got 1A plus 2C is equal to 1, that's going to be 1A plus 2 times 5/17 is equal to, I'm going to write this as 17/17. So we get 1A, that's 10/17. Bring that to the other side, we get 7/17. Okay, let us then go to the other ones. We've got B and D to solve. I'm going to start with those two equations. We get 1B plus 2D is equal to 0. And minus 5B plus 7D is equal to 1. If I multiply this by 5 and add those together, we get 0. We've got 17D, and we've got 1. So D is going to be 1/17. And then I've got to plug that back in order to solve for B. I'll use the first one, that seems easier. 1B plus 2/17 is equal to 0. And when I solve that, we get B is equal to -2/17. The other thing that I notice is that all these things are divided by 17. I can factor out a 1/17, and when I do that, I've got 7, -2, 5, and 1. And you might notice that these are similar to the numbers we had in the beginning, which is kind of cool. All right. So here we've got another bunch of examples of matrices that are inverses, and what I'd like us to notice is that we have some of the same patterns going on. We can see that, for example, the first one all has 7s in the bottom, and otherwise the numerators are the same thing from the beginning, but maybe switched around a little bit. I notice that 3 and 1 here have switched places, and if I take a look at like the next one, we've got 3 and 7 becomes 7 and 3. This one's a little bit harder for us to kind of figure out just because we're in decimal form. So we're going to hold off on that for now. And the last one's, oh, well, we're switching those again. So that kind of makes sense there. Maybe. So I'm going to call the matrix A, B, C, D. And the first thing I'm going to do is say swap A and D. That seems like it's something that's happening here. Second thing I notice is that the B and C positions are staying the same, except something is changing about them. They're all changing signs. So I'm going to make a second step here. Say multiply B and C by -1. And then we need a third kind of piece of this to figure out what this thing that we're dividing by here is. And the way I'm going to do this, I'm going to take a look at the numbers I have in my matrix and try to figure out how to get 7 from them. I could do like 3 minus -4, and that would get me 7. But then it would be like 3 plus 2 is 5, and I can't do different operations. All right, I know we had some stuff with diagonals before, so let's talk about those. So here, if we do this, it would be 3 and -4. But if I did 3 minus -4, that would be 7. Okay. Going this way, I've got 21 and 16. And if I did 21 minus 16, I get my 5. If I do this, I've got 16, and I've got 15. If I do 16 minus 15, I've got 1, and that might be why those didn't show up. So here's the thing with all of these. I'm going to multiply by 1 over this weird number that's, I'm going to classify this as AD minus BC. And I'm also going to give this weird thing a name. I'm going to call this the determinant, and this is just going to be for a 2x2 matrix. For bigger matrices, we have to have some other ways to do this. But for a 2x2, it's always going to be the same thing. Oh, look, and here we've got some determinant stuff. So I'm going to do that same thing. I'm going to take those two forward diagonal and do -8. From that, I'm going to subtract the backward diagonal. I'm actually going to write this out as products just so we can see where things are coming from. So it's going to be -2 times 4 minus -2 times 0. So -8 minus 0 is -8. Here we've got 1 times -1, that's my forward diagonal, minus my backward diagonal, 1 times 0, which is -1. Those are the determinants of these matrices. Oof. That's a hard word to say early in the morning. All right, so then to find the inverse of each matrix, that's the next step here. that's going to combine the stuff that we just did. So I'm going to call this the determinant of A to talk about this as matrix A. And on the inside, we're going to swap our A and D, and we're going to make B and C negative. That's the shortcut for this. We can also do that solving systems that we did earlier. That's a really good idea. But let's just take a look. So we've got 0 minus 2 is negative 2. 1 over negative 2 goes out front. I'm going to swap my A and D, 0, negative 9, make the other ones negative. At this point, we're done. If we were to multiply these two matrices together, this would give us the identity 1, 0, 0, 1, which is really useful for us. Same things here. I'm going to do my determinant, and I've got negative 8 minus 0 is, sorry, positive 8 minus 0 is 1 over 8. And then we're going to swap our inside terms, negative 4, negative 2, and make these guys negative, negative 4, and negative 0 is just 0. That's that inverse. The last thing we're going to do is to think about this in a way that is helpful to us. So we're going to use inverses to solve matrices. This is like dividing by a number that's multiplying. We're going to do the same thing here. The one thing we got to be really careful of is that we have to multiply in the same direction. So if I'm going to have this matrix negative 3, 3, negative 6, 0 times something x, I'm just leaving a little bit more space there. If I'm going to multiply by the inverse, there's some directionality here. I'm actually only going to do one of these two just because it's a little bit messy to try to fit both of these on the same page, and this is already going to be a long video. I've got to multiply on the same side, so I'm going to left multiply by this inverse, and the determinant is going to be negative 9 minus negative 6. Negative 9 minus negative 6 is going to be negative 1/3 out front. On the inside, we're going to swap our top and bottom things. We're going to make our inside B and C the opposite values, so 6 and 0. I'm going to do the same thing here. I am going to multiply this in just to make this a little bit faster for myself. So we get negative 1, negative 2. Wow, I can't multiply. 1 and 0. So then when we do our matrix multiplication here, we end up getting negative 9 plus 0 is negative 9. We've got negative 12 plus 0 is positive 12. We've got negative 18 plus negative 6 is going to be negative 24. And when we multiply over there, we've got positive 24 plus 0. That's our final matrix. On the left side, this would end up being 1, 0, 0, 1 when we multiply two inverses together. And we talked about that if we multiply the identity by another matrix, we get that matrix out. So this would tell us that we have 1x equals this matrix. This is our final answer here.